Hello students, in today's session we'll discuss about how to do the time delay calculation in the 8051 microcontroller. While writing the assembly language programs, many times we need to call the delay routine. Then how to find out the exact time delay for any particular routine that can be understood after completion of this session. We need a delay in many applications like in the stepper motor or in the keyboard interface to provide the key debounce period. We need the time delay, or in the applications like traffic controller where the green, red and yellow light time duration for turn on and off that is to be decided. So in such applications, how to calculate the exact time delay so that we can introduce the time delay required as per our need. To understand that, first of all, let us understand what is machine cycle. In the 8051, there are total 12 clock cycles for one machine cycle. So the operating frequency, if we consider 12 megahertz, then the time period is 1 upon 12 F oscillator. So that is approximately 1 microsecond. That is the time required for one machine cycle. Here in the diagram you can see there are total 6 states for entire one machine cycle, beginning from S1 to S6, and each state is divided into 2 phases, phase 1 half and phase 2 half, and total 12 clock cycles that are required for one machine cycle. So that is how 1 microsecond that will be required for 12 megahertz crystal. You can exactly calculate the time delay for execution of instructions by the knowing how many machine cycles are required for that particular instruction. Let us consider a 2-byte instruction here where you are accessing the external core memory. Now in the timing diagram, you can see though it is a 2-byte instruction, but requires still only one machine cycle. The ALE signal that is activated twice in a machine cycle, you can see here, and the PSEN signal that is activated, it is going low here. That means it is used as a read strobe for accessing the external core memory, and second time here it is going low, active, right? So during the first part, whenever ALE goes high, you can see the PCH means program counter higher byte and TCL means lower byte. The 16-bit address that will be available on the common bus. And then in the latter part, you can see the opcode that is fetched for the instruction. And here the second byte that is fetched. So that is how read operation with the external memory that is performed in a one machine cycle by the 8051 microcontroller. Similarly, let us understand how to access the external RAM. You know, MOVX instruction that is used for accessing the external RAM. Now here the instruction is for read operation, MOVX A, add DPTR. And here it is the write operation, whatever the data in the accumulator that will be written at the memory location specified by the data pointer. So read and write operations using the MOVX instruction. To understand how MOVX instruction is executed, let us see how this read operation is performed. Now here, to access the external RAM, RD signal, read signal that is used as the read strobe. And now here again you can see the opcode fetch cycle. ALE, here you can see the ALE is activated twice in a machine cycle, and the opcode is fetched in the first machine cycle, and here the data is read from that location. pointed by DPTR. So DPH and DPL is the data pointer contents, and that is how the data that can be read. So that shows the timing diagram for BOOYAX instruction, specifically a read operation. In case of write operation, instead of RD bar, you have to use WR signal, write bar signal, and then the data that is to be written has to be placed on the data lines, and then when it completes the write cycle, the data will be written at the memory location pointed by DPTR. Okay. So that is how the read and write cycles that are performed by the 8051 microcontroller. Now, while writing the programs, so you must know how many machine cycles that are required for that particular instruction. The machine cycle, which we already discussed, is nothing but the clock cycles, say 12 clock cycles that constitutes the one machine cycle. If we consider the crystal of approximately 11.0592 megahertz, then the total frequency, that is 1 upon time period. So you can see here that one machine cycle lasts 12 oscillator periods. So to calculate the machine cycle, we'll take 1 upon 12 of the crystal frequency and then take the inverse of its result in the time period. There are different microcontrollers having different crystals used. Here you can see the three examples in which 11.0592 megahertz crystal is used, then 16 megahertz, and then for 20 megahertz crystal. So you will get the different time periods for one machine cycle. 1.085 microsecond for, let us say, 12 megahertz crystal. Here you can see the 0.75 microsecond for 16 megahertz crystal and 0.60 microsecond for 20 megahertz crystal. Okay. So that is the time required for one machine cycle. Now we mainly consider the crystal that is having approximately 12 megahertz operating frequency for our calculations. So if we consider that, here are some examples given, different instructions which are having one or two machine cycles. Now here you can see the multiply instruction is having 4 machine cycles. Require more machine cycles. Only multiply and divide are the instructions which requires 4 machine cycles. Otherwise, most of the instructions in the 8051 you will see that requires only 1 or 2 machine cycles. Now from that you can calculate how much time is required for that particular instruction. So whenever it is a one machine cycle, then 1.085 microsecond is the time required. If it is the 2 machine cycle required, let us say DJNZ instruction. Now in that case, 2.17 microsecond is the time required. Similarly for L jump and S jump. Now if it's just a no operation, that is used for just inserting a delay of 1.085 microsecond. And here for multiply, you can see 4 into 1.085 gives you 4.34 microsecond. So that is how you can first find out how many machine cycles are required and how much time is required for executing single instruction. Now, once you understand this, let us go through a small delay routine to understand how the delay is calculated. Now here is the program where initially the 55 data that is taken in the accumulator and outputted on port 1. Then a delay is called, then complemented the data in the accumulator, and jump is used here again. So alternately, the data will be flashed on the port 1. And for that, here you can see the delay routine is called using the absolute call instruction. Now let us see what is the delay routine. In the delay routine, you will find that the R3 register is loaded with the count, and then DJNZ instruction is used, which requires 2 machine cycles. This requires 1 machine cycle, and the loop is here only. RET requires 1 machine cycle. Okay. So to find out how much delay this delay routine will introduce. Let us go through the next slide. Here you can see the 1, 2, and 1 machine cycles required for the 3 instructions in the delay routine. And then you can find out the exact delay using this. 255 is the count loaded in the R2 register. So the instruction DJNZ that will be executed 255 times and requires 2 machine cycles. That's why 2 into 255 plus 1 plus 1, that is the machine cycles for first and last instruction, and into 1.085 microsecond, that is the time for 1 machine cycle. So gives you total 555.52 microsecond delay. This is the simple, you can how to calculate the delay. Let us consider this routine where initially the R2 that is loaded with the 255 count and few NOP instructions are used, and again DJNZ instruction is used for introducing delay. So you can increase the time delay using such loops. Write down the machine cycles required for each instruction and then do the calculations. Now for here loop, 255 into 1 plus 1 plus 1 plus 1 plus 2, that is the time required for each instruction, machine cycles required for each instruction, and into 1.085, that will give you 1660.05 microsecond. The time delay of the 2 instructions outside the loop then will be 1660.05 plus 1 into 1.085 microsecond. That gives you 1803.32425 microsecond. So that is how you can calculate the exact time delay that can be introduced with that delay routine. To understand how to insert more delay, you can use the nested loops that is shown here. You can see the 2 registers are used here to load the count, and there are 2 loops. One is the here loop and next is the again loop. Again, write the number of machine cycles required for each instruction. You can see here DJNZ requires 2 machine cycles. The other instructions requires only 1 machine cycle. Now for here loop calculation, just 1 plus 1 plus 2, right? So into the loop will be executed here loop 250 times. So into 250 into 1.085 microsecond gives you 1085 microsecond. Now here again loop calculation. In this loop, move R3 comma hash 250 and DJNZ R2 comma again. The 2 instructions at the beginning and end of the again loop, that will add 1 plus 2 into 200 into 1.085 microsecond. So gives you 651 microsecond to the time delay. So that much time delay has to be added. So the again loop repeat the here loop 200 times. You can see the R2 is 200. So 200 into 1.085 microsecond gives you 217000 microsecond, and as a result of that, the total time delay will be 217000 microsecond plus 651 microsecond. That will give you 217651 microsecond, or that is equivalent to 217.651 millisecond. So that's how you can calculate the exact time delay for any delay routine, or you can add the delay as per your requirement with increasing the count and increasing the loops. So that is how you can use the nested loops to add more delay in the loop, in the program. So that is how you can do the delay calculations. and can be smartly used in your programs for controlling different devices. Thank you.